you can help. People probably struggle to visualize a little bit when you say like data center in space. Like we're not going to slap engines on a building and fly it up there. Like these actually look like pretty different. And so kind of walk through how you take something that's in a giant building on the ground and turn it into something that's functional in space.
Yeah, I think it's pretty interesting. A lot of people don't actually know what the inside of a data center even looks like, right?
Yeah,
and
it's some like mythical place where the internet's in the cloud or something.
Yeah, some people envision wires, some people envision boxes, but like effectively it comes down to a set number of chips and the things that we need to launch into space are actually quite small when we look at it. The more challenging part is figuring out how do you get the power for it, and that's where a lot of what we've worked on for existing like Starlink technology, the solar arrays, are what we want to utilize that expertise to be able to build a satellite that can actually launch the critical components of the data center into space itself. We like to look at this and say like, what is the actual engineering problem here? And it's really a combination of delivering power and then taking the waste heat and energy away and sending it into the vacuum of space, as you mentioned.
Yeah. Now the AI satellite is actually much simpler than a Starlink satellite. A Starlink satellite has gigantic phased array antennas. It's got parabolic antennas. It's got a lot of laser links. It's much more complicated than an AI satellite. An AI satellite is essentially a lot of solar cells, a radiator, and you still need some laser links, but you don't have all of the super complex antennas that you have on a Starlink satellite. So, I mean, given the two, the easier one to design for is the AI satellite.
Yeah.
It's just a little bit bigger.
It's bigger.
Just make stuff bigger, yeah. I was like, so we've got, this is our AI-1, if you guys want to walk us through.
Yeah. So the first thing that we're really looking at here is like, first you've got to make something compelling, right? And we thought that the right place to start is around the 150 kilowatt like peak power level. But as we look at the workloads with our experience with xAI, we get to actually see that we can also support about 120 kilowatts of average compute. There's a difference.
Yeah. What we're showing here is kind of a draft version of the version 1 of the SpaceX AI satellite, the AI-1, I guess you could call it. And seems like a reasonable place to start is 150 kilowatts peak power, 120 kilowatts sustained power, and to give you a sense of what does that actually look like in terms of the size of the radiators, size of the solar panels. The assumptions here are 250 watts per square meter for the solar array, and about 1,400 watts per square meter for the radiators. So the radiators, these are double-sided. Radiators are radiating both sides. They're oriented knife edge to the sun, and it's 1,400 watts per square meter is a very achievable goal. Over time, we think we can probably do above 250 watts per square meter and above 1,400 watts per square meter for the solar panels and radiators, respectively. But this gives you like this is pretty much what the satellite's going to look like.
Yeah.
It's a lot of solar panels, radiator, and then everything else is pretty small by comparison.
And these are like evolutions of things that we have actually already launched in our Starlink constellation to date.
Yeah.
That's really, I think, the cool part to me is that we're looking at solar technology that we already are going to use on the V3 Starlink vehicle. So I'm like really excited to then just take those and make it bigger.
Yeah, part of what we want to convey here is that there's not some magic that's necessary that doesn't exist for the AI satellites. As Ian said, a lot of this is technology we've already made for the Starlink V3 satellites. So we basically don't think this is a super hard problem compared to things we already do. Mm-hmm. There would also be probably something on the order of a terabit of connectivity, of laser link connectivity from the satellite. Mm-hmm. The 150 kilowatt peak power level roughly matches what, say, an NVIDIA GB300 rack would do. So if you've got a GB300 with 72 GPUs. Its peak power, I think, is around 140 kilowatts. But it's almost impossible to get it to be at that peak power. A more reasonable operating envelope would be around 120 kilowatts average power. But it can peak up to 150. So it's basically, think of it as a rack of compute in space. And then you can connect these racks of compute to either each other via the laser links or directly to the Starlink constellation.
Yes.
So you can close the link with the Starlink constellation, and then Starlink can then send that data to the ground using the existing Ka and Ku antennas on the vehicle. It also has laser links to the ground.